Good morning, chaps. This is week 13, I think, and I hope you guys are enjoying your time at school. This week, we're going to really finish the chapter of, not of calculus, but of differentiation. I'm going to give you one lesson, which is going to be quite long, where we're going to test differentiability, okay? And then the next lesson I'll give you is basically just another time for revisions. It's the last exercise of the chapter where you just put everything together. And I might give you some more time next week. We will have a test at some point, possibly even next week. But I will be in touch with you on that on the WhatsApp. So, yeah. Right, so testing differentiability. So a lesson, before we got into differentiation, we were talking about continuity, and we said that functions are either continuous or not continuous. And then there's two kind of discontinuities. There's removable and jump discontinuity. So today we're going to learn about what is a differentiability. What does it mean when a function is differentiability? So I'll just give it to you straight away. A function is differentiable at a specific x, let's say x equal a, if, first of all, it has to be continuous. So if it's not continuous, then it definitely can't be differentiable. Okay? But that's just one condition. Okay? The second condition is that you've got a value for the derivative of f. What is the definition of a derivative? Is the difference in the y divided by the difference of the x, right? Where the difference of the x, the limit of the difference of the x, approaches 0. But there's a big difference here. See, this is what I wrote here. I wrote the definition of the derivative of f, okay, at a. But the difference is that I say that here, h approaches plus 0, 0 from the plus side. And here, h approaches 0 from the negative side. Okay? And what more than those, I need to have both this limit and that limit, and more than that, those two limits are equal to each other. Okay? What does that mean? Okay, let me try and explain. So let's say I have a point, this is x equal a. Okay? Now when I want to find out the value of the derivative at a, I basically take another point, which is a plus h, okay, a bit to the right, okay, I'm adding an h, a positive h to the a. I find the values of the y. This one will be f of a plus h. This is f of a, okay. I find the delta y, okay, that's the delta y, and I divide it by the h, but the delta x, which is h. That's the value of the derivative. And the last thing, I make h become 0. So I get, in other words, I get these 2 points close. But we always work with the second point, a plus h being to the right of a. Okay? In other words, we said h is positive. Okay? So h is getting close to 0, but from the positive side. It's 0,000000001 plus. Okay? Now, in the same way, we could have done it the other way around. We could have had a negative h. Okay? We could have had another one, which is also, we'll call it f plus a, f of a plus h. But now our h is negative. Okay? It's a negative h. It's not positive h, it's a negative h. And these will be our 2 points. And then we'll have f of a and f of a plus h. And it's f, yeah, it should be an f. Okay? It's going to be the difference between these two. Okay? And I'm going to divide it by that h. Okay? But now our h is negative. Okay? So this, okay, this one, okay, is going to give us the derivative of f of a by calculating the second point being to the right. Here I'm calculating the derivative at a with using the second point to the left. Okay? So both cases I'm calculating the gradient. I'll use another color. The gradient to the gradient of the tangent to the curve. That's what the derivative is. The gradient of the tangent to the curve. But here in the blue side, I'm using second point to the right, and the red I'm using second point to the left. Okay? So I'm finding the gradient a little bit to the right or a little gradient gives you the same answer, then we say it's a differentiable function. Okay? And that's kind of makes sense. Okay? If continuous function, okay? And when we're talking about continuous function, I said just imagine you have some tiny little person with tiny little feet, and he walks around and he doesn't have any jumps and any huge steps to jump over. If he can walk up like that, that's continuous. Well, differentiable, it has to be continuous, but also what that little guy doesn't like having, he doesn't like having like huge sudden change in the gradient. I'm going to make it a little bit more obvious. So let's say I have something like this, and then at some point I have like a very steep gradient. So it goes from 0 to like 5. Okay? The gradient change suddenly. Okay? If there is a sudden change in the steepness, that might be continuous. This is a continuous function, but it's not differentiable. Because if I'm looking at that point, if I'm getting to calculating the gradient of the curve here, I might get, this is let's say a straight line, okay? I might get 5, 5, 5, 5. And if I just move past that point, suddenly it's half, okay? It goes from 5 to half. There's no middle way, okay? That is continuous, but not differentiable, okay? The limit for the gradient, for the derivative, exists from the positive and from the negative, but it's not the same derivative. Okay? Now I know that was a lot of abstract talk. Obviously now we're going to do some examples, so just wait here, don't go away. Okay, so our first example, you can find page 89. Okay, we've got this step function. We've got two parts. Okay, 2x plus 3 minus x squared plus 2. They change at minus 1. And we first of all want to draw the graph, then say are they continuous in minus 1 and are they differentiable. Okay? Bear with me. Okay? Right, so let's start from minus 1. Okay? Anything smaller than minus 1, with x is smaller than minus 1, then the function is simply 2x plus 3. So I'm going to just put minus 1 here. Okay? And maybe I'll start by substituting minus 1. If I put minus 1, minus 2 plus 3 is 1. So at minus 1, y is equal to 1. Okay? It's a full dot because that includes the minus 1. And then before minus 1, it's a straight line, isn't it? 2x plus 3, it's a straight line. Okay? So a straight line that has a positive gradient, so it goes like this. Okay? Where does it cross the x-axis? When is y equal 0? When x equal minus 3 over 2, right? If I put minus 3 over 2, divide by 2 minus 3. Okay, so it's minus 1.5. So minus 1.5, when x is equal minus 1.5, y is 0. Okay? Now let's look at to the right of minus 1. That's obviously a parabola. Okay? It's a negative before the square, so it's a sad face. Okay? So from here, okay, I'm just going to draw a sad face. And something like that. So we need to find out where does it cross. When x is equal 0, okay, that's going to be 2. Okay? And when is it going to cross the y-axis? Is when, sorry, the x-axis is when y is 0. When is y 0? So x have to be, I have to put square root 2. Okay? If I put square root 2 and I square it, I get a 2. And then I've got that minus here. So this is its square root 2. Okay? So what? We drew it. Okay? We've got it. We've got a function that's made out of a straight line and a parabola. Okay. Now, is it continuous at fx equal minus 1? Okay, so x equal minus 1. This is the point of content. That's obviously the point where these two functions come together, the stitch I call it before. So I need to find out if it's continuous. How do I know if it's a continuous? Well, it will be continuous. First of all, I need to find the limit, okay, from to the right and to the left of x minus 1. Find that there is a limit, okay, and that limit is equal to the value of the function at x minus 1. It also needs to be defined. So let's start by actually finding what is f of minus 1. We actually already did that. It is defined. We use this definition. It's equal to plus 1. Okay? Now let's look for the limits. Okay? Limits of f of x when x approaches minus 1 on the negative side. Okay? So if I approach from the negative side, I have to use that function. So it's going to be 2 times minus 1 plus 3, which we already found is 1. Okay? It's basically the value of the function. Okay? Now, we'll do the same thing. Okay? The value of the function, but now x approaches minus 1, but now from the positive side. So I'm using this definition. So I'm going to put minus 1 squared plus 2. So it's going to be minus 1 squared is 1. So it's going to be minus 1 plus 2. And I still get 1. So I showed that the value, if f is defined in minus 1, equal 1. And that's equal to both limits, whether I go from the right to the left. So it is continuous, yeah? Okay? Definitely continuous. Okay? Right, pause here. I will raise this and we'll talk about, is it differentiable or it's at minus 1. Okay, to figure out if this function is differentiable, I need to use the definition to find the derivative by using positive h and negative h when I make h equal to 0. As close as possible to 0, but one's a little bit of positive, the other one a bit negative. In other words, I'm trying to find out the gradient to the right of that point and to the left of that. And if that gradient is the same, then it's differentiable. So I'll start with a positive h. So the value of the function of minus 1 at minus 1, x equal minus 1, plus a tiny little h, okay, h being positive, 0 plus, minus f minus 1 divided by h. So now I just have to value. If I'm having h a little bit positive, okay, that means I'm to the right of minus 1. So it's a little bit, x is larger than minus 1, right? F minus 1 plus h, okay, is h being positive. That means x is a little bit larger than minus 1. So I have to use this definition. So I'm going to just put minus 1 plus h here. So it's going to be minus 1 plus h squared. Yeah, I'm not forgetting that minus. Plus 2. Minus f minus 1. Right. Now the value of f and minus 1, we already found what it was when we were looking for the continuity. It's simply 1, right? F minus 1, doesn't matter where you find, because it's continuous, it's always going to be minus 1. It will be 1, positive 1, but I've got that minus, so it's minus 1. Defining that by h, and not forgetting that limit, which I always forget, that's 0 plus. Okay? Right, now we need to open that. So keep that minus there. Minus 1 squared is plus 1. Minus 2h, right? That is minus 1 times 2 times minus 1 times h. Plus h squared. Okay? Plus 2 minus 1, it's plus 1. Divided by h. Not forgetting, again, this deletion. H approaches 0. Plus. Equal. Okay, now, limits. Let's not remember that one. H plus 0. Okay? I've got minus, so it's minus 1 plus 2h, just turning the minus into plus, minus h squared plus 1 divided by h equal limit h approaches 0 plus. Okay, the minus 1 minus 1 cancels. Okay, I'm just going to take h out as a factor. Okay, so I'll take h out. I've got 2 minus h divided by h. H cross cancels. Okay? And I've got I'm left with 2 minus h. But obviously, at this point, once I got rid of the denominator, I'm not scared anymore, and I can just put h equals 0. So 2 minus 0, the answer is 2. Okay, the answer is 2. Okay? Now, I think, let's just write 2. Okay, I'll write it down here. Limit limit f a minus 1 plus h plus, we said we got 2. So I'm going to keep that on the side, okay, and make some space. Okay, so now I'm going to find out what's the derivative to the left of x equal minus 1. So I've written the same definition, but now h approaches 0 from the left. So it's minus 0.0000000. Okay? So then I must use x smaller than minus 1. So I'm going to use this definition. It's going to be 2 times minus 1 plus h plus 3. Okay? So I'm using that definition. Minus f minus 1. We already know that the value of the function of minus 1 is simply 1. Okay? Divide by h, and look at that. Again, I forgot the limit. Limit h approaches 0 minus. Okay. This is a bit easier, isn't it? So I've got minus 2 plus 2h plus 2 divided by h. Not forgetting the limit. Okay? 2 minus 2 cancel out. They always do. Okay? And then I'm also cancelling out the h, and I'm going to get 2, which is the same as it was there. Okay? So I calculated by the definition the limit of the derivative on either side of our point x equal minus 1, and in both cases I got 2. Okay? So it is differentiable. It's continuous and it is differentiable. Okay? Now you can see that here. You could have seen it before where at that point it's not just that it's continuous. If I have a little person with tiny little feet, it's not just continuous. Actually, the gradient changes continuously as well. There is no jump in the gradient. The gradient here was 2, and the gradient just at x equal minus 1, okay, when I move from here to there, is also 2. Okay? So, cool. Let's do another video for the second example because this lesson is getting a bit too long. See you in the next lesson.